Hello, juniors. Today we're going to start with the last topic that we're going to cover for logic and statistics for this year, and it's called the normal distribution. And it has to do, once again, with probability. Up to now, we have seen one type of probability distribution, which is the binomial distribution, okay? In which we analyzed events which had only two possible outcomes, either a success or a failure. And for today, we're going to learn about this new type of distribution, which is called the normal distribution, which is a type of probability distribution which is widely used in different real-life applications. Okay, so it says, the objectives for the class: number one, define a normal distribution; number two, represent the normal curve distribution in a diagram; and finally, calculate probabilities using normal curve distribution. I'm going to be showing you how to properly use a calculator to find probabilities of normal curve distribution. So, what is a normal distribution? It says it's a function that represents the distribution of many random variables as a symmetrical bell-shaped graph. So this is how a normal distribution looks like. You see that most of the values are bunched or are grouped into the center, right? While we have few information in the extreme values. So it says, it is considered to be one of the most important distributions in statistics, since it is a suitable model for many naturally occurring variables. So examples of normal distribution are physical attributes of peoples, animals, and plants, right? For example, height, weight, etc., right? Height and weight are both normally distributed. If you try to think about the people, right? Maybe if you wanna consider people between 15 to 25 years old, and you calculate or you ask each of lots of people their heights and weights, you would get to the conclusion that both variables, height and weight, are both normally distributed, meaning that most of the people would have the center values, right? While there will be very few people in the extreme values. So that's why physical attributes of people are generally have a normal distribution. Then also mass-produced items from factories. Whenever, let's say we have a hamburger factory, which needs to do 500-gram burgers each time, right? So machines are calibrated in a way in which the cut of the meat will be done such that the meat will weigh 500 grams, right? But there's always certain uncertainty from the machines, right? They're not 100% precise. So some of the cuts may have a little bit less than 500 grams. Some cuts may have a little bit more than 500 grams. But normally it will be most of the values would be somewhere around 500 grams, right? We're gonna see some examples about that later on. Then student exam scores is also normally distributed. Generally, people tend to score in the average values, and very few people have very good scores and few people have very bad scores, right? Then time to complete a task is also a normal distribution. Reaction times is also a normal distribution. This is a very good topic for a math project, for example. And also IQ scores. These are just some examples of how a normal distribution can be presented. Okay, in each of these cases, these three properties apply. Number one, the curve is bell-shaped. That's this curve over here. Then it is symmetrical about the mean. That means that if the mean is in the middle, the mean is in the middle, we have the same shape here, right? It is symmetrical about the mean. Then the mean, mode, and median are the same. We're going to do an experiment later on in order to prove this. But basically what we're saying is that in a normal curve distribution, which we assume that is perfect, right? We're making an assumption that the sample is a perfect sample, right? Whenever we do experiments, you would see that it's not 100% a perfect bell-shaped curve. It has some tendency to either side. But in a perfect bell-shaped curve, the mean, median, and mode all lie in the middle, okay? Exactly in the middle. Okay, So those are some things to consider. Then it says, if a random variable x has a normal distribution with mean this is called mu, it's a Greek letter, mu, and the standard deviation sigma, this is written as, and this is how we represent a normal distribution. It means x is normally distributed with a mean value of mu and a variance of this value, right? It's always expressed as mean and variance. If you remember from binomial distribution, we would say that a variable is binomially distributed with n number of trials and a probability of success p. This is how we represent a binomial distribution. But to represent a normal distribution, we use this notation, where we need to write the mean and the variance of the spread of the values in our example, right? So it says, remember that the mean, mu, is the average and the standard deviation, sigma, is a measure of spread. Then it says, note that in the expression, x has a normal distribution with mean, mu, and variance. Sigma squared is the variance. Remember that the variance is the standard deviation squared. Okay, so that's just for you to remember. And it says, mu and sigma are called the parameters of the distribution. The mean is the central point of the distribution, and the standard deviation describes the spread of the distribution. The higher the standard deviation, the wider the normal curve will be. We're going to see this in the following example right here. So it says, look at these two graphs and pay really close attention in order to understand what's happening here. It says, these three graphs show one binomial distribution, the green one, which is this one, this binomial distribution, the red one, and finally the blue binomial distribution, normal distribution, this one over here, right? Do you see the difference here? In all of the three cases, we have the same variance, right? But we have different means, right? And what does that represent in our graph? It just represents that our bell-shaped curve is displaced. You see that all of them are exactly the same shape, right? But they are displaced either to the right or to the left. Why? Because the center of each normal distribution is given by the mean, right? So whenever we have the same variance but different mean, what we're doing is we're displacing or we're moving our bell-shaped curve either to the right or to the left, depending on the problem, okay? So it says, the standard deviations are all the same, so the curves are all the same but the mean of the first is less than the mean of the second, which is less than the mean of the third normal distribution. Now, what happens if I keep the same mean, but I change the standard deviation or variance? What will happen in this case? Take a look at the following graph. It says, these three graphs show x is normally distributed with a mean of 5 and a variance of 1. x2 is normally distributed with a mean of 5 and a variance of 4. And x cubed is normally, and x3 is normally distributed with a mean of 5 and a variance of 9 or standard deviation of 3. And it says here, the means are all the same and the curves are centered around this, but standard deviation of 1 is less than standard deviation of 2, which is less than standard deviation of 3. So the curve x1 is narrower than x2 and x2 is narrower than x3. So take a look at this. You see that all of them have the same center. They all share the same mean, which is 5 in this case. But we see that the green curve is narrower than the blue, than the red one, which is again narrower than the blue one, right? Why does that occur? The smaller the standard deviation, the narrower the curve will be. Why? Because there will be less spread of the information. Most of the information will be bunched up in the middle, right? While in this case, where the standard deviation is bigger, it's 3 times bigger than the green bell-shaped curve, we see that there is a lot of spread between the information, and because of that, the normal distribution is much more wider, right, than the green one, which is the narrowest. Okay, so that's something that you need to understand, right? It says the curves may have different means and or different standard deviations, but they will have the same characteristics. all of the characteristics that we mentioned here are always applied independently of the values of the mean and standard deviation whenever we talk about a normal distribution. Let's read this international minus. This is just for cultural information. The normal curve is also known as the Gaussian curve. It is named after the German mathematician Carl Friedrich Gauss, who used it to analyze astronomical data. This is seen on the old 10 Deutsche Mark notes. So you see that in this currency, there's a normal curve distribution. This is just for general information. Okay, I want to show you this experiment. I'm leaving the link here for you to try it on your own, but I want to show you what this is about. It's basically what we were just talking about, changing the mean and standard deviation of the normal curve distribution. So if you open the link, you would be right on this page, which is Desmos, right? And you see that we get a normal curve distribution here, which has a mean of 0, and we have a spread of 1 according to this problem, okay? So it says here, in the function below, A is the standard deviation and B is the mean. So B is 0, A is 1. By changing the values, you can see how the parameters for the normal distribution affect the shape of the graph. Remember, the area under the curve represents the probability. We're going to be seeing this in a second. But basically, if A is our standard deviation, we would see that if we increase A, the value of A, then this curve must become wider, right? And this top value should become lower, right? So let's see. If I change, you see that as I increase the value of the standard deviation, the curve becomes wider and wider and wider, right? If I go back and I leave it in 1, it will stay like this, right? But what will happen if I change the value of the mean? If I change the value of the mean, the whole bell shape will be displaced, right? If I change it to the right, it must be displaced to the right. For example, if I change mean to 1, you see that it moves 1 unit to the right, and so on, right? 3, 4, 5, 6, 7, 8, and so on. And if I move it to the left, same thing, right? So that's the effect of changing, the mean and the standard deviation of a normal curve distribution, right? You can play this, and let's change both at the same time. You see that they are both getting displaced and they change shape in both cases. Okay, so that's what I want to show you. So if we go back to the assignment, we will continue with the theory about normal distribution. Then it says, the area beneath the normal distribution curve. This is very important because it's the main application of normal curve distribution. It says, no matter what the values of the mean and the standard deviation are for normal probability distribution, the total area under the curve is always the same and equal to 1. Okay, so if we draw this normal curve distribution, for example, the area under the curve is always representing 100% of our information. So that's something very important you must remember. Then it says, we can therefore consider partial areas under the curve as representing probabilities. And in this example, for example, if we want to calculate the area of the blue shaded region, this area would be a value which is less than 1, right? And we're going to be finding in this case the probability of x, a variable x, being less than 5, right? From 5 below, we're talking about probability of x being less than 5, okay? And if I want to find this area over here, this would be the probability of x being greater than 5, okay? We're going to see that later on with exercises. Okay, so that's one thing to consider. Then it says, so in this normal distribution, we could find the probability of x being less than 5 by finding the shaded area on the diagram. That's what I just told you. Unfortunately, the probability function, the equation of the curve for the normal distribution, is very complicated and difficult to use. So if you want to model this red line over here, then the function that describes that red line is all of this, which looks kind of messy, right? And we're not going to be using this function, but we're going to be using the properties of the curve in order to find probability. So don't worry about this. This is just information. Maybe if you want to analyze that function in your math projects, that could be a good idea. But for now, we're not going to consider this function to solve the exercises, okay? You see that the domain of this normal curve is from negative infinity to positive infinity. That means that if I zoom in into this function, it means that this red line is still continuing towards negative infinity and is still continuing here towards positive infinity, right? The straight line y equals 0 is a horizontal asymptote to this curve, okay? But the area beneath the curve between as we go to negative infinity or to positive infinity is very small, so we consider it to be 0, right? So we do not consider those values anymore. Okay, then it says, it would be too hard for us to use integration to find areas under this curve. However, there are other methods we can use, and that's what we're going to be learning. Okay, here's a very important thing about the normal curve distribution. If you look at this graph, you would see that it has a mean of 0 and a standard deviation which is equal to 1 in this case, right? Because we're considering one standard deviation here, one standard deviation here. Okay, so if you look at the curve and let me see something. Okay. And if we consider one standard deviation to the right and one standard deviation to the left, by theory, we are considering 68.27% of our information. Okay, this is something that you don't need to know, but maybe if you're analyzing things without calculator, it's important to know these values. Okay, then if we consider from the mean 2 standard deviations to the right and 2 standard deviations to the left, then we are grabbing 95.45% of our information. And finally, if we grab 3 standard deviations to the right and 3 standard deviations to the left, we're grabbing 99.73% of our information. So almost 100% of our information. So if we want to find some statistical value or probability of something, depending on the level of confidence that we want to work with, we would decide whether to work with 1 standard deviation, 2 standard deviation, 3 standard deviation, or whatever we decide is more convenient for us, okay? But these values always apply to a normal curve distribution, okay? So that's also important to consider. Then it says, the standard normal distribution. This is a special type of normal distribution, which you will see its importance later on when we work with exercises. But for now, we're just going to be defining what this standard normal distribution is about. It says, the standard normal distribution is the normal distribution where the mean is equal to 0 and the standard deviation is equal to 1. So this is always true when we're talking about a standard normal distribution. It would always have a mean of 0 and a standard deviation of 1. Always, whenever we talk about standard normal distribution. So it says, the random variable is called C. It uses C values to describe the number of standard deviations any value is away from the mean. So the standard normal distribution is written as C has a normal distribution where the mean is 0 and the standard deviation or variance, in this case they're the same, is equal to 1, okay? So you see the difference, right? Whenever we talk about any type of variable, instead of C, we write X, okay? But whenever you see the letter C instead of X here, it means that we're talking about the standard normal distribution, which is a particular example of a normal distribution. Why is it particular? Because it always has a mean of 0 and a standard deviation of 1, okay? So here it is. The standard normal distribution always has a mean of 0 and a standard deviation of 1. So if we plot this, we do a bell-shaped curve, the mean would be at 0 and then the standard deviation is 1, right? We don't need to plot that in the normal curve. Finally, it says you can use your GDC to calculate the areas under the curve of a standard normal distribution for values between A and B, and hence we can find the probability of C, a value C, being in between A and B. We're going to be looking at this more in depth with some examples later on, okay? Let's see if we can do this already. Maybe we can work with some exercises. Or I'm gonna leave this for part 2, okay? I'm just gonna do the theory for now, and we're gonna see exercises about how to apply the normal distribution in the next class, okay? So I'm gonna leave the class here. I hope this was clear. As I told you, we just covered the theory, but I think it will be clear for you when we touch the practical part of this in order to apply all of these different concepts that we have covered. So I hope it was clear, and if not, please let me know. We're going to clear doubts in future live sessions. Thank you for your attention and see you.